Assalamualaikum and hi to all. My name is Zaliana Suha binti Zulfatah with student ID of 1900033. Currently, I'm taking Basin analysis courses at University Technology Petronas. So, today I would like to present technical paper review of the high resolution sedimentary filling in Qiondonan Basin, northern South China by Zhongjian Shao, Zhenshen, Zhenfen Wang, Jinpeng Sen, Jinbao Liu, and Qiu Mizan. The Qiondonan Basin, up to the southeast of Hainan Island, is an important Cenozoic sedimentary basin with rich oil and gas resources. It lies in the intersection of northwest side slip zone of Red River Fault and also northeast trended reef belt of northern continental margin of South China Sea. The objective of this research is to conduct a study on the sedimentary filling of Qiondonan Basin in high resolution by using few methods. The basin basically covers an area of 8.4 by 104 km square with water depth spanning between 100 to 2,800 meters. It begins to reef after 45 million years ago, especially after 34 million years ago, and stopped at 21 million years ago. The study area contains of three sets of major faults that developed during the Sin Reef periods, which is 45 to 25 million years ago, and controlled the basin architecture wholly. Not only that, it also consists of four tectonic belts known as Northern Depression Belt, Central Uplift Belt, Central Depression Belt, and lastly Southern Uplift Belt. From the diagram above, we can see that there are 8 Cenozoic stratigraphic units have been identified and named by CNOOC. This will include Eocene formation in the 45 to 36 million years ago, Cation formation in early Oligocene, Liushu formation in late Oligocene, Sanyang formation in early, Meishan formation in middle Miocene, Liu formation in late Miocene, Yanshan formation in Pliocene, and lastly Ledong formation in the Quaternary. Moving on to the next part is the methods used in order to obtain data and result for this study. The high density and high resolution data source offer valuable opportunity to elaborately disclose the features and history of sediment filling in Qiondonan Basin in 3-dimensional scale. Also, this will accurately calculate the sediment budget during Cenozoic. In order to recover the sediment thickness, time depth conversion and the compaction process has been done. VSP data from the well used for the time depth conversion methods. On how the data source has been taken, a total of 500 2D and 3D high-resolution multi-channel seismic reflection profiles and 42 wells including VSP data and logging data provided by CNOOC has been taken. The seismic profile have reached the density of 2 km by 6 km, which covers an area of 6.4 by 104 km square with the common midpoint gathers placed every 12.5 meter and vertical resolution of 25 to 35 meter along each profile. The 19 sequence boundaries of each seismic profile have been traced and interpreted in geoframe workstation with the age calibrated by the industrial wells and micropaleontology. Consequently, 21 wells were selected from 42 wells, of which the interval velocity were calculated and the trend of velocity versus time and depth was explored. Then, the form of time depth conversion function was determined and fitted to each other. From the graph displayed, we can see that velocity increased with time linearly, holding the same increment for the left side, which is diagram A, while in diagram B, velocity increased with both depth but decreased in the increment. You can see that the data in the graph above are not fit, hence 2-order polynomial, 3-order polynomial, and lastly power functions were proposed to fit the observed data, which were tested and compared by fitting the observed time data of well YC2112 in the northwest of Qiondonan Basin, of which the oldest strata are early Miocene. So the formula used can be seen in the slide above of 2-order polynomial, 3-order polynomial, and power functions respectively. First, the two-way time is less than 3 seconds. Then within the top graph, we can see that the d poly 2 and d poly 3 was fitted but little deviated in the power functions. So changes has been made in the two-way time and now become 8 seconds and got almost perfect fit graph. The velocity of power function increase with time and decrease in the increment which deviates from the observed trend. Nevertheless, it provides us the appropriate velocity and depth for deep-seated strata. Although the velocity for two-order polynomial increase linearly with time in B, which is compatible with the observed trend, it indeed predicts the extremely large velocity and depth for deep-seated strata. The velocity of three-order polynomial increases with time and holds a rising increment in B, which significantly deviates from the observed trend and leads to the extraordinarily large velocity and depth for deep strata. For the C diagram, the extended velocity depth curves in the form of three functions for deep-seated strata are all in agreement with three of the observed velocity depth trend. Additionally, as the coefficient of the third order term is negative and the second order term is positive, it inevitably causes the velocity inversion at depth. Consequently, the power function with the exponent between 1 and 2 is the best choice for predicting the depth for deep-seated strata where the drift cannot reach. The compaction method is a process where the porosity was reduced and pore water was exposed. There are direct consequences of the compaction under its own weight during burial. So how the process has taken place? So firstly, the porosity versus depth of 38 wells were calculated from the sonic and density logs. Because of the Q&A basin mainly consists of shale and sand, hence the formula that used are as above for porosity of shale, and the second one is the porosity of sand. The initial porosity of shale in Q&A basin is 69%, way more larger than in the sand, which only 43%. The porosity reduction of shale with depth is rapider than in the sand. The porosity loss of the shale mainly occurs above depth of 2 to 2.5 km, corresponding to the physical compaction stage, and unimportant below 4 km. However, the porosity reduction of sand is still remarkable at the depth of 5.2 km. The next part of the presentation is the result obtained from the study. So sediment rates of extreme strata has been illustrated. So how the author do this? They divide the sediment volume by duration of each stratum. The average sedimentary accumulation rates were obtained by dividing the sedimentary accumulation rates by data cover area. So from this, the author realized that the sedimentation in Q&A basin experiences three stages of rifting, which are C-rift, early post-rift, and lastly late post-rift. The diagram in the slides shows that the depot center trapped by the sediment rate contour of 200 meter per million year in C-rift stages are separated by uplifts. The sediment rates are beyond 400 meter per million year in the central depression, with largest value of more than 600 meter per million years in Ledon site in the west, while the sediment rate of Beijiao site is merely 200 meter per million year. It shows in the diagram that there are a long curved depot center confined by the sediment rate contour of 200 meters per million years developed in the early post-rift stage. The sediment rate increased from east to west with the largest value of more than 400 meters per million years still in the Ledon site. For the late post-rift, the depot center located at the west with largest sediment rate of more than 700 million meter per million years. For the late post-rift, the depot center located at west with largest sediment rate of more than 700 meter per million years, adjacent to the one of the major port, and almost no sediment deposits in the east during the late post-rift. The three stages of rift are summarized under diagram D, where we can see the migration of depot center gradually to the west during Cenozoic is well illustrated by the sediment rate contour of 200 meter per million years. The sediment rate in the west segment is higher than in the east segment, especially in the late post-rift stage, which is 10.5 million years ago until today. The sedimentation principally focused on the west. The three stages of result and summarized under diagram D, where we can see the migration of the placenta. For the A diagram, the sedimentary accumulation rate of Basin by the sediment in the 200 meter per million rate. The sediment rate in the west segment is higher than in the east segment, especially in the late post-stream stage. This paper with 10 paper that studied by Cliff and signed in the year 2006. The sedimentation principally focus on, and we can see that there are the stages of changes in the comparison between the three where we can see the migration of the placenta gradually. In conclusion, the objective of paper to study the sedimentary filling in Basin was achieved. From this, we can understand that the distribution of sedimentation in deep water is mainly controlled by the sediment sources and transportation routes. There are also three reef stages that has been identified that control the basin architecture, which are St. Reef, early post-reef, and also late post-reef. For the recommendation part, I recommend to state the objective of the study clearly. This is because the aim of the study only can be visualized when reading the whole content. Not only that, it is a slight ambiguous in this discussion part where the author makes a comparison between the Basin and Yingge Basin. However, in overall, the research paper is excellent with lots of diagrams that helps to visualize the subsurface condition of Basin better. I think that's all from me for this paper review. Thank you.